Imagine holding a simple object in your hand, a stone, a coin, or even your phone. It feels solid, ordinary, completely harmless. But hidden inside the atoms that make up that object is an astonishing secret. Locked within its matter is an enormous amount of energy, far greater than anything we encounter in everyday life. In fact, according to modern physics, a tiny amount of matter could release energy equivalent to thousands of tons of explosive power. Yet the world around us does not constantly erupt with this energy. Tables remain tables. Mountains stand still. And the air around us stays calm. Somehow, nature has found a way to hide an immense reservoir of energy inside every atom and keep it perfectly stable. This idea fascinated physicists like Richard Feynman, because when you truly understand the atom, you begin to see the universe differently, not as a collection of solid objects, but as energy quietly locked inside matter. When we hear the word atom, it is easy to imagine something like a tiny solid ball, a miniature version of the objects we see around us. For a long time, even scientists pictured atoms that way, small, indivisible particles, forming the building blocks of matter. But as physics progressed in the early 20th century, experiments revealed something deeply surprising. The atom is not a solid particle at all. In fact, its structure is so strange that it almost defies our everyday intuition. The first shock came when scientists discovered that atoms are mostly empty space. At the center of every atom lies a nucleus, an incredibly small region containing protons and neutrons. Around this nucleus move the electrons, but the scale of this structure is astonishing. If you were to enlarge an atom until it was the size of a massive sports stadium, the nucleus would be no larger than a tiny grain of sand sitting at the center of the field. While the electrons would be somewhere near the outer seats, everything in between would be almost completely empty. This means that the solid objects we see around us are not really solid in the way we imagine. The atoms that make up a table, a rock, or your own body are mostly empty space, held together by invisible forces. The reason things appear solid is because of the interactions between electrons and the electromagnetic forces that prevent atoms from passing through each other. But structurally speaking, matter is far more spacious and mysterious than our senses suggest. Yet, despite this emptiness, nearly all the mass of an atom is concentrated in the nucleus. Electrons contribute very little to the atom's total mass. The real weight of matter comes from the protons and neutrons tightly packed together at the center. And this tiny nucleus is extraordinarily small compared to the atom itself. Typically, the diameter of an atom is about 100,000 times larger than the diameter of its nucleus. In other words, if the atom were the size of a city, the nucleus would be no larger than a small marble. This discovery completely changed how physicists thought about matter. Instead of being tiny solid balls, atoms turned out to be delicate structures with most of their volume empty and almost all their mass squeezed into an incredibly compact center. Richard Feynman loved pointing out how counterintuitive this is. To our senses, matter feels firm, denser, and stable. But if we could see the atomic structure directly, the world would look more like a vast collection of tiny solar systems floating in space. The electrons move according to the strange rules of quantum mechanics, forming probability clouds rather than neat circular orbits, while the nucleus sits at the center containing the heavy particles. And inside that tiny nucleus lies something even more remarkable. The protons within the nucleus all carry positive electric charge. According to the laws of electromagnetism, objects with the same charge repel each other. In principle, the protons should push away from one another violently, causing the nucleus to fly apart. Yet this does not happen. The nucleus holds together with incredible strength. This is because another force of nature is at work, the strong nuclear force. This force is one of the fundamental forces of the universe, and it is enormously powerful at extremely short distances. It acts like an invisible glue, binding protons and neutrons tightly together inside the nucleus and overcoming the electrical repulsion between protons. Without this force, atomic nuclei could not exist, and matter as we know it would be impossible. What makes this even more fascinating is that the strong nuclear force operates only over a very tiny range. It becomes powerful only when particles are extremely close to each other. That is why the nucleus can remain stable while still being incredibly small. The particles must stay tightly packed for the force to hold them together. As physicists studied the nucleus more closely, they began to realize that this tiny region was not just important for the structure of atoms, it was also the place where enormous amounts of energy were hidden. The particles inside the nucleus are bound together by what physicists call binding energy. This energy is not visible in everyday life because it is locked into the structure of the nucleus itself. But under certain conditions, when the nucleus changes its structure, part of that hidden energy can be released. And when that happens, the amount of energy involved is vastly greater than anything produced by ordinary chemical reactions. Understanding the strange structure of the atom therefore reveals a profound truth about the nature of matter. The objects we interact with every day may look simple and stable, but deep inside them lies a complex architecture of forces, particles, and energy. Matter is not just passive substance. It is a dynamic arrangement of tiny components held together by some of the most powerful forces in the universe. And at the center of every atom, inside that unbelievably small nucleus, nature has quietly stored a tremendous amount of energy, waiting to be understood. At first glance, the nucleus of an atom seems like a simple cluster of particles packed tightly together. It contains protons, which carry positive electric charge, and neutrons, which carry no charge at all. These particles are collectively known as nucleons, and they sit at the center of the atom, forming an incredibly small but dense core. But when physicists began studying the nucleus more carefully, they realized something extraordinary. The way these particles are bound together reveals the true source of nuclear energy. To understand this, we must look at the forces acting inside the nucleus. Protons all carry the same positive charge, which means they naturally repel one another through the electromagnetic force. If electromagnetism were the only force at work, the nucleus could never exist. The protons would push away from each other violently, and atomic nuclei would immediately fall apart. Yet in reality, nuclei are remarkably stable. Something must be holding these particles together with tremendous strength. That something is the strong nuclear force. The strong nuclear force is one of the fundamental forces of nature, and it is incredibly powerful at very short distances. When protons and neutrons are extremely close together, this force pulls them toward each other and binds them into a stable nucleus. It acts like an invisible glue, overcoming the electrical repulsion between protons and keeping the nucleus intact. But the existence of this force leads to a deeper and more surprising question. Why does binding particles together involve energy in the first place? This is where one of the most famous ideas in physics enters the picture. In 1905, Albert Einstein introduced the equation E equals mc squared, which revealed that mass and energy are actually two forms of the same thing. According to this principle, mass can be converted into energy, and energy can also appear as mass. The two are interchangeable. When physicists began applying this idea to atomic nuclei, they discovered something remarkable. If you measure the total mass of all the individual protons and neutrons that make up a nucleus, and then compare it to the mass of the nucleus itself, you find a small but important difference. The nucleus actually weighs slightly less than the combined masses of its separate particles. This missing mass is called the mass defect. The obvious question is, where did that mass go? The answer is that it has been converted into energy. When the protons and neutrons bind together to form a nucleus, part of their mass transforms into what physicists call binding energy. This energy is stored within the structure of the nucleus itself, holding the particles together. In other words, the nucleus is not just a collection of particles. It is a system where mass has been partially converted into energy that acts like a powerful internal glue. This binding energy is the true origin of nuclear energy. As long as the nucleus remains intact, that energy stays locked inside. But if the structure of the nucleus changes, if it splits apart or combines with another nucleus, the balance of binding energy changes as well. When that happens, some of the stored energy can be released. And because the conversion between mass and energy involves the enormous factor c squared, where c is the speed of light, even a tiny amount of mass can produce a tremendous amount of energy. This is why nuclear reactions are so much more powerful than chemical reactions. Chemical reactions involve only the rearrangement of electrons around atoms. The nuclei themselves remain unchanged, which means the enormous binding energy inside them stays locked away. Nuclear reactions, however, involve changes to the nucleus itself. When the structure of the nucleus is altered, a portion of the binding energy can be released, often in the form of high-energy particles and radiation. The difference in scale is staggering. A single nuclear reaction can release millions of times more energy than a typical chemical reaction between atoms. This realization fundamentally changed how scientists understood matter. Matter was no longer just inert substance occupying space. Instead, every atomic nucleus represented a tiny reservoir of stored energy. The mass of the nucleus itself was partly a manifestation of this energy, bound into the structure by the strong nuclear force. Richard Feynman often emphasized how strange and beautiful this idea is. When we hold an object in our hands, we usually think of it as solid matter, but at a deeper level, what we are really holding is energy arranged into stable structures. The mass of the object is not simply stuff, it is a measure of how much energy is locked inside the particles that compose it. The nucleus of an atom therefore hides an incredible secret. Within its tiny dimensions, forces of immense strength bind particles together, converting mass into energy and storing it in the form of nuclear binding energy. Under normal circumstances, that energy remains trapped, quietly maintaining the stability of matter. But under the right conditions, when nuclei are rearranged through processes like fission or fusion, a fraction of that hidden energy can escape. And when it does, the results reveal just how powerful the energy inside matter truly is. If every atomic nucleus contains such an enormous amount of energy, an unsettling question naturally follows. Why doesn't everything around us constantly explode? After all, the atoms in the air, the ground beneath our feet, and even the atoms inside our bodies all contain nuclear binding energy. If that energy were suddenly released, the consequences would be unimaginably violent. Yet the world around us appears calm and stable. Mountains stand for millions of years. Tablets remain solid. The atoms in our bodies quietly hold together throughout our lives. The reason lies in a delicate balance of forces and a remarkable feature of nature. Nuclear energy is extremely well locked inside the structure of the nucleus. To understand why matter does not spontaneously explode, we must look again at what is happening inside the nucleus. A nucleus is a crowded place where protons and neutrons are packed incredibly close together. But the particles inside it are subject to two powerful and competing forces. The first is the electromagnetic force, because protons carry positive electric charge. They repel one another strongly. The closer they are pushed together, the stronger that repulsion becomes. If this were the only force acting in the nucleus, it would be impossible for protons to remain together. The nucleus would instantly fly apart as the protons pushed away from each other. Yet this does not happen because another force operates at extremely small distances. The strong nuclear force. The strong force is vastly more powerful than the electromagnetic force, but it acts only when particles are extremely close together, roughly the size of the nucleus itself. When protons and neutrons are packed tightly enough, this force binds them together with tremendous strength. In a stable nucleus, these two forces reach a kind of balance. The electromagnetic force is trying to push the protons apart, while the strong force is pulling the particles together. As long as the strong force dominates within that tiny region, the nucleus remains stable. This balance creates a deep well of stability that keeps the nucleus intact. Physicists sometimes describe this idea using the concept of an energy barrier. Imagine a marble sitting at the bottom of a deep bowl. The marble has energy stored in its position, but it cannot escape unless it is given enough energy to climb over the edge of the bowl. Atomic nuclei behave in a similar way. The particles inside them sit in a stable configuration that is extremely difficult to disrupt. Even though large amounts of energy are stored inside the nucleus, that energy cannot simply escape on its own. Something must first supply enough energy to overcome the barrier that keeps the nucleus stable. This is why most atoms in nature can exist for billions of years without breaking apart. Their nuclei are trapped in stable configurations where the balance of forces prevents spontaneous change. Only certain heavy elements have nuclei that are naturally unstable, slowly decaying over time through radioactive processes. But even these decays happen gradually, often over extremely long time scales. The important point is that nuclear energy is not easily released. It is locked behind the structure of the nucleus and protected by powerful physical constraints. Richard Feynman often emphasized how remarkable this stability really is. The universe contains enormous energy stored in matter, yet nature has arranged things in such a way that this energy is normally inaccessible. Everyday events like dropping a rock, lighting a fire, or smashing two objects together do not disturb atomic nuclei. The energies involved in ordinary chemical processes are far too small to affect the nucleus. Chemical reactions only rearrange electrons around atoms. The nucleus remains untouched, and the vast nuclear energy inside it stays safely locked away. Releasing nuclear energy requires conditions far more extreme than those found in everyday life. In nuclear fission, for example, a heavy nucleus must first absorb a neutron in order to become unstable enough to split. In nuclear fusion, two positively charged nuclei must be forced extremely close together, overcoming their natural repulsion. Both processes require specific circumstances and significant input energy before the hidden energy inside the nucleus can be unlocked. In this sense, the stability of matter is not an accident, but a fundamental feature of the laws of physics. The forces inside the nucleus create a system that is both incredibly powerful and remarkably secure. Vast amounts of energy are stored in every atom. Yet the universe has constructed a mechanism that keeps this energy contained. Without this stability, matter would not exist in any recognizable form. Atoms would constantly break apart, and the complex structures that make up planets, oceans, and living organisms could never form. The calm and solid world we experience every day is therefore the result of an extraordinary balance deep within the atomic nucleus. Hidden inside every atom is a reservoir of immense energy, but nature has built an almost perfect lock to keep it safely contained. For billions of years, the enormous energy inside atomic nuclei remains quietly locked away. The balance of forces inside the nucleus keeps matter stable and prevents that energy from escaping. But under certain circumstances, this lock can be broken. When that happens, the energy hidden inside the nucleus can be released in a sudden and dramatic way. One of the most important processes that unlocks this energy is known as nuclear fission. Nuclear fission occurs when a heavy atomic nucleus splits into two smaller nuclei. This process does not normally happen easily because the nucleus is held together by the strong nuclear force. However, some very heavy elements, such as uranium or plutonium, sit near the edge of stability. Their nuclei are large and crowded with protons and neutrons, and the balance between the strong force and the electrical repulsion of protons becomes more delicate. In these heavy nuclei, the strong nuclear force still holds the particles together, but the electromagnetic repulsion between the many protons is also very strong. The nucleus is therefore somewhat unstable, like a tightly stretched object that can break if disturbed in the right way. One of the simplest ways to disturb such a nucleus is by introducing a neutron. Neutrons carry no electric charge, which means they can approach the nucleus without being repelled by its positive charge. When a neutron collides with the nucleus of an atom like uranium, 235, the nucleus can absorb it. For a brief moment, the nucleus becomes heavier and more unstable. Instead of remaining compact and balanced, it begins to stretch and deform. Physicists often compare this to a drop of liquid that starts to wobble and elongate. If the disturbance is large enough, the nucleus can split into two smaller fragments. When this splitting happens, several things occur simultaneously. First, the original nucleus breaks into two lighter nuclei, which fly apart at extremely high speeds. Second, a few additional neutrons are released during the process. And third, a large amount of energy is liberated. This energy comes from the change in nuclear binding energy between the original heavy nucleus and the two smaller nuclei that are produced. The total mass of the fragments and emitted particles is slightly less than the mass of the original nucleus and the incoming neutron, according to Einstein's relation E equals mc squared. That small difference in mass is converted into energy. The amount of energy released in a single fission event is enormous compared to ordinary chemical reactions. A typical chemical reaction might release a few electron volts of energy per atom, while a nuclear fission event releases around 200 million electron volts. This means that atom for atom, nuclear reactions can produce millions of times more energy than chemical ones. That is why the splitting of atomic nuclei can generate such immense power. But perhaps the most remarkable feature of nuclear fission is what happens to the neutrons that are produced during the split. When a uranium nucleus undergoes fission, it typically releases 2 or 3 new neutrons. Each of these neutrons can then collide with another uranium nucleus, causing it to split as well. When this process repeats over and over again, it creates what physicists call a chain reaction. In a chain reaction, one fission event triggers several more, which in turn trigger even more. The number of reactions grows extremely quickly. If the conditions are right, this can lead to an explosive release of energy in a very short time. This principle lies behind the immense destructive power of nuclear weapons. However, the same physical process can also be controlled and used for peaceful purposes. In nuclear reactors, engineers carefully regulate the chain reaction so that the energy is released gradually rather than all at once. Control rods absorb some of the neutrons, slowing the reaction and preventing it from accelerating uncontrollably. The heat produced by the fission reactions is then used to generate steam and produce electricity. In this way, the energy locked inside atomic nuclei can be harnessed to power entire cities. Richard Feynman often emphasized how astonishing this discovery was. For most of human history, people believed that the energy available to us came mainly from chemical processes such as burning fuel. The idea that enormous energy was hidden inside the very structure of matter itself was almost unimaginable. Yet nuclear fission revealed that even the smallest pieces of matter contain vast reservoirs of energy waiting to be released under the right conditions. When the delicate balance inside the nucleus is disturbed in just the right way, the lock that holds nuclear energy in place can break, and when it does, the energy that has been quietly stored within matter for billions of years can suddenly emerge with extraordinary power. When scientists first discovered nuclear fission, it revealed that enormous energy could be released by splitting heavy atomic nuclei. But the universe had already been using nuclear energy long before humans understood it. In fact, the most powerful and important energy sources in the cosmos operate through a different nuclear process altogether. The stars themselves shine because of nuclear reactions occurring deep inside their cores. Every ray of sunlight that reaches Earth is ultimately the result of energy released from atomic nuclei in the heart of the sun. To understand how this happens, we must look at the conditions inside a star. A star forms when a massive cloud of gas in space collapses under its own gravity. As the cloud contracts, the material becomes denser and hotter. Eventually, the pressure and temperature in the core grows so extreme that something extraordinary begins to occur. At temperatures of millions of degrees, atoms can no longer remain intact. The electrons are stripped away, leaving behind bare atomic nuclei moving at incredible speeds. In the sun and most other stars, these nuclei are primarily hydrogen nuclei, which consist of a single proton. Under normal conditions, two positively charged protons would strongly repel each other because of the electromagnetic force. This repulsion creates a barrier that normally prevents them from coming close enough to interact through the strong nuclear force. But inside the core of a star, the situation is very different. The temperature is so high that the nuclei move with enormous kinetic energy, constantly colliding with one another. At the same time, the immense gravitational pressure of the star forces the particles extremely close together. Occasionally, two protons approach closely enough that the strong nuclear force takes over. When this happens, the protons can fuse together in a process known as nuclear fusion. In the sun, this process occurs through a series of steps that ultimately convert hydrogen into helium. First, two protons combine, forming a heavier particle and releasing energy. Through several intermediate reactions, 4 hydrogen nuclei eventually merge to create one helium nucleus. During this process, something remarkable occurs. The total mass of the helium nucleus produced is slightly smaller than the combined mass of the 4 hydrogen nuclei that went into the reaction. Just as in nuclear fission, the missing mass has been converted into energy, according to Einstein's equation, E equals mc squared. That energy is released in the form of high-energy particles and radiation. Over time, this energy makes its way from the core of the star to its surface and eventually radiates into space as light and heat. This process is what powers the sun and every other ordinary star in the universe. Every second, the sun converts roughly 4 million tons of mass into energy through nuclear fusion. That energy spreads outward in all directions, warming planets, driving weather systems, and providing the light necessary for life on Earth. When we feel the warmth of sunlight on our skin, we are experiencing energy that was created by nuclear reactions deep inside the sun millions of years earlier. What makes nuclear fusion particularly fascinating is that it produces energy in the opposite way from nuclear fission. Fission releases energy by splitting very heavy nuclei into smaller ones. Fusion releases energy by combining very light nuclei into heavier ones. In both cases, the key idea is the same. Certain nuclear configurations are more stable than others when nuclei rearrange themselves into a more stable structure. The difference in binding energy is released. In the case of stars, fusing hydrogen into helium leads to a more tightly bound nucleus, and the excess energy is emitted as radiation. This simple process has enormous consequences for the universe. Nuclear fusion inside stars is responsible for producing much of the energy that fills the cosmos with light. It also plays a crucial role in the creation of chemical elements over the lifetimes of stars. Fusion reactions build heavier elements from lighter ones, gradually producing the atoms that later become part of planets and living organisms. The carbon in our bodies, the oxygen we breathe, and the calcium in our bones were all formed through nuclear reactions inside ancient stars. Richard Feynman often pointed out how extraordinary this realization is. The light that allows us to see the world around us, the warmth that sustains life, and even the elements that make up our bodies all originate from nuclear processes taking place inside distant stars. The same forces that bind protons and neutrons inside atomic nuclei are responsible for the brilliance of the night sky. In a very real sense, the universe is powered by the energy hidden inside the simplest particles of matter. The stars shine because the atomic nuclei within them are constantly rearranging themselves, releasing the energy that had been locked inside since the beginning of the cosmos. For most of human history, the enormous energy hidden inside atomic nuclei was completely unknown. People relied on far simpler sources of power: burning wood, into oil, and other fuels that release energy through chemical reactions. These reactions rearrange electrons between atoms, producing heat and light, but they barely touch the immense energy locked inside the nucleus itself. Only in the 20th century did scientists begin to realize that matter contained a far deeper reservoir of energy. Once nuclear fission was discovered, humanity found a way to access a small portion of that hidden power in nuclear reactors. Heavy nuclei, such as uranium, 235, are split through controlled chain reactions, releasing large amounts of heat that can be used to generate electricity. Today, nuclear fission provides energy for cities and industries across the world. Yet even as this technology developed, physicists recognized that fission was only part of the story. The most powerful nuclear process in the universe is not fission but fusion, the same process that powers the stars. If humanity could learn to harness nuclear fusion on Earth, it could unlock a source of energy far greater and potentially far cleaner than any technology currently available. The idea is simple in principle, but extraordinarily difficult in practice. Fusion releases energy when very light nuclei combine to form heavier ones. The most promising reaction for practical use involves isotopes of hydrogen, such as deuterium and tritium, which can fuse together to form helium, while releasing enormous amounts of energy. The difficulty lies in forcing these positively charged nuclei close enough together for the strong nuclear force to bind them. Under normal conditions, the electromagnetic repulsion between the nuclei pushes them apart before they can get close enough to fuse inside stars. This barrier is overcome by extreme temperature and pressure. In the core of the Sun, temperatures reach about 15 million degrees Celsius, and gravity compresses the plasma to extraordinary densities. These conditions allow hydrogen nuclei to collide with enough energy to occasionally overcome their electrical repulsion and fuse together. Reproducing similar conditions on Earth is one of the greatest technological challenges humanity has ever attempted. To make fusion possible, scientists must heat a gas of hydrogen isotopes to temperatures even hotter than the center of the Sun. At such temperatures, the gas becomes a plasma, a state of matter, where electrons are stripped from atomic nuclei and particles move freely at enormous speeds. But no ordinary container can hold a plasma that hot. Any material wall would instantly melt. To solve this problem, physicists developed methods of containing plasma using powerful magnetic fields. One of the most advanced designs is the tokamak, a device that uses magnetic fields to trap plasma in a toroidal or donut-shaped chamber. Inside this chamber, magnetic forces guide the charged particles in circular paths, preventing them from touching the walls of the reactor. By heating and compressing the plasma within this magnetic cage, scientists attempt to create the conditions necessary for fusion reactions to occur. Another approach uses extremely powerful lasers to compress tiny pellets of fusion fuel. In these experiments, lasers strike a small target from multiple directions, creating intense pressure that squeezes the fuel inward. For a brief moment, the conditions inside the pellet resemble those found in the cores of stars, allowing fusion reactions to begin. These experiments have achieved remarkable progress, but maintaining stable and efficient fusion remains a formidable challenge. The goal of fusion research is to reach a point known as ignition, where the fusion reactions themselves produce enough energy to sustain the process without requiring more energy input than output. Achieving this balance has proven extremely difficult. Plasma is unstable and tends to develop turbulent motions that disrupt the conditions needed for sustained fusion. Even small instabilities can cause energy to escape before the reaction becomes self-sustaining. Despite these obstacles, scientists around the world continue to pursue fusion as a long-term energy solution. Projects such as large international fusion reactors aim to demonstrate that controlled fusion power is possible on a practical scale. If successful, fusion could provide an almost limitless supply of energy using fuels that are abundant in nature. Deuterium can be extracted from seawater, and the reactions themselves produce far less long-lived radioactive waste than traditional nuclear fission. Richard Feynman often admired the boldness of scientific ambition, and the quest for fusion is a perfect example of that spirit. Humanity is attempting to recreate in a controlled laboratory environment the same nuclear process that powers the stars. It is an effort to unlock the energy hidden within the simplest atoms in the universe and use it to sustain civilization. Although the challenge remains immense, the pursuit itself reflects one of the most remarkable aspects of human curiosity. By studying the forces that shape the universe, we are gradually learning how to harness the same fundamental processes that light up the cosmos. When we look around at the world, everything appears solid, stable, and familiar. A table feels firm under your hand. A mountain stands unmoving for thousands of years. Your own body seems like a collection of solid matter that simply exists. Our everyday experience gives the impression that matter is something permanent and substantial. But modern physics reveals a much deeper and stranger truth at the most fundamental level. Matter is not just stuff, it is energy, arranged and locked into stable forms. This idea was captured in one of the most famous equations ever written, E equals mc squared. Einstein's equation tells us that mass and energy are not separate things. They are two expressions of the same underlying reality. Mass can be thought of as energy that has become concentrated and bound into a stable structure. The atoms that make up everything around us are not merely collections of particles. They are systems in which enormous energy is stored within the nucleus through the binding of protons and neutrons. Under normal circumstances, that energy remains hidden. The strong nuclear force holds the nucleus together so effectively that the energy stays locked inside for billions of years. As a result, the world appears calm and stable. But once we understand the physics of the atom, we begin to see matter in a completely different way. What appears solid and permanent is actually the result of delicate balances between forces and energy. Richard Feynman often emphasized how astonishing this realization really is. The ordinary objects of everyday life are not fundamentally ordinary at all. They are incredibly complex arrangements of particles and forces, quietly holding vast amounts of energy inside their structure. When you hold a small object in your hand, you are holding far more than a piece of matter. You are holding energy that has been locked into a stable form by the laws of physics. The mass of the object is essentially a measure of how much energy is contained within it. In nuclear reactions, we occasionally glimpse this hidden reality when a heavy nucleus splits or when light nuclei fuse together. A tiny fraction of mass disappears and reappears as energy. The amount of mass involved is extremely small, yet the energy released can be enormous. This is a direct demonstration of the deep relationship between mass and energy. It shows that matter is not the static substance we once imagined, but rather a concentrated form of energy held in place by the structure of atomic nuclei. The same principle applies everywhere in the universe. The light from distant stars is produced by nuclear fusion, converting mass into energy. The elements that make up planets and living organisms were forged through nuclear reactions inside stars long before the Earth existed. Even the atoms in our own bodies carry within them the same hidden energy that powers the sun. In this sense, every piece of matter is part of a much larger story about the transformation and organization of energy in the universe. What appears to us as stable matter is simply one stage in that ongoing process. Feynman had a remarkable ability to communicate this sense of wonder about the natural world. He often reminded people that understanding physics does not make the universe less mysterious or beautiful. Instead, it reveals layers of reality that are far more astonishing than our everyday intuition suggests. The idea that matter is frozen energy is one of those revelations. It tells us that the solid world we experience is actually built from dynamic processes at unimaginably small scales. Protons and neutrons bound together by powerful forces, electrons forming quantum structures around them, and energy quietly stored within the architecture of the nucleus. The calm surface of the world hides a universe of intense activity and immense energy. Yet nature has arranged these forces in such a way that matter remains stable and predictable, allowing complex structures to exist. Without that stability, stars could not form, planets could not exist, and life could never emerge. The same forces that store enormous energy inside atoms also create the conditions that make the universe livable. When we finally step back and look at the bigger picture, a remarkable idea emerges. Everything we see around us, every rock, every ocean, every living organism is made of atoms whose mass represents energy bound into stable forms, matter, in the deepest sense, is not separate from energy at all. It is simply energy that has been captured, organized, and frozen into the structures we call the physical world. And once you begin to see the universe this way, the ordinary objects around you start to feel a little less ordinary, because hidden inside them is one of the most profound secrets of physics.